Let us continue ionic equilibrium. In the ionic equilibrium, we have seen a titration between sodium carbonate versus HCl. Sodium carbonate versus HCl titration. Sodium carbonate we have taken a 50 cc. Concentration is a 0.05 molar. Okay. HCl we have taken how much in the sense 0.1 molar. Now, we have added HCl from the burette to the conical flask solution. Now we have to see pH of the each place, then we can find which indicator is suitable for this. Sir, okay. Now volume of HCl is 0 ml while pH of conical flask solution is 11.5. HCl added 5 ml while pH is 10.93, we can say. HCl added 10 ml, pH of solution is 10.51. HCl added up to 15 ml, pH of solution is 10.15. HCl added totally 20 ml, pH of solution is 9.73. HCl is added up to 22.5 ml, pH of solution is 9.38. 25 ml added, pH is how much in the sense 6.95. We said this is called equivalence point, we said. This is what in the sense equivalence point. Equivalence point we said. Okay. Next, we will add HCl continuously. We will add still more amount of HCl. Suppose we are adding 5 ml of HCl. What is the pH of solution? 5 ml additionally we are adding. So this 5 totally becomes how much in the sense 30 ml. 30 ml of HCl is added. What is the pH of solution? That we will see. Okay. Initially what we have taken in the sense 50 cc of sodium carbonate. Concentration is 0.05 molar. Concentration 0.05 molar. Sodium carbonate we have taken. We are multiplying these two. We are getting millimoles of sodium carbonate. Millimoles of sodium carbonate. We got this much. Sorry. We added HCl. HCl totally how much added in a sense? 30 ml is added. What is the concentration? Means 0.1 molar. So on multiplying these two, we are getting millimoles of HCl. That is how much in the sense 3 millimoles of HCl we got. Okay. From the sodium carbonate, the carbonate is going for reaction. From the sodium carbonate is taking added H plus from HCl and becomes what in the sense bicarbonate. Okay. In the sodium carbonate, the carbonate takes H plus from HCl and becomes bicarbonate. Sorry. This carbonate, how many millimoles? Millimoles means 2.5 millimoles. H plus how many millimoles means 3 millimoles. H plus 3 millimoles. Sorry. How much carbonate is reacting in the sense 2.5 millimole will react, remaining is 0. H plus will react 2.5 mole, remaining is how much in the sense 0.5. Remaining is 0.5 millimole, we can say. Bicarbonate is how much produced in the sense 2.5 millimole is produced. Bicarbonate 2.5 millimole is produced. Then this bicarbonate takes the remaining H plus. This bicarbonate takes this H plus and becomes what in the sense H2CO3, carbonic acid. This bicarbonate takes this H plus and becomes carbonic acid. Bicarbonate how much in the sense 2.5 millimole. H plus how much in the sense 0.5 millimole. So how much H plus is reacting in the sense 0.5 millimole is reacting, remaining is 0. Bicarbonate reacting 0.5 millimole, remaining is 2 millimole. Carbonic acid produced how much in the sense 0.5 millimole. 0.5 millimole of carbonic acid is produced. Sorry. Now the resultant solution. In the resultant solution, what is present in the sense bicarbonate is present and carbonic acid is present. Carbonic acid is weak acid. Bicarbonate is its conjugate. This weak acid conjugate. Carbonic acid we can say weak acid. Its conjugate we can say bicarbonate. Therefore, the resultant solution is what in the sense acidic buffer we can say. Resultant solution we can say acidic buffer. For acidic buffer, how to find pH? Based on Anderson equation. Anderson equation says pH is equal to pKa plus log salt by acid. Salt by acid. So, what is the acid here? Acid is a carbonic acid H2CO3. What is the salt here? Salt in the sense this weak acid conjugate is a salt. Part we have to consider. This weak acid, its conjugate we have to consider in the place of salt. Therefore, in the place of salt, we are considering bicarbonate. Okay. Then in the pKa, Ka is there. This Ka is Ka1 or Ka2. How to know it? Ka1 or Ka2. How to know it in the sense? For that, you see this one. This H2CO3 net charge is neutral. It is univalent. This anion is having univalent charge. Therefore, it is univalent. The net charge is 0. Therefore, here difference is 1H plus. Therefore, we can say this here Ka1 we can say. Therefore, pH is equal to pKa1 plus log bicarbonate by carbonic acid. Like that we said. Now we will substitute the terms. We will substitute pH is equal to pKa1, that is minus log Ka1. Ka1 is how much in the sense 4.47 into 10 to the power of minus 7 plus log bicarbonate we have to substitute. Bicarbonate is how much in the sense 2 millimole. Bicarbonate is 2 millimole. Carbonic acid how much in the sense 0.5 millimole. Carbonic acid is 0.5 millimole. By simplifying this, we are getting pH. pH is how much in the sense 6.95. Okay, so we got pH of the solution. That value we will write here. So on adding totally 30 ml of HCl into the conical flask solution, the pH of the solution becomes 6.95. Let us add further. So totally we added 35 ml now. So pH of solution is 6.53. Totally we added 40 ml so far. pH is 6.17. Totally we added 45 ml so far. pH is 5.75. Totally we added 47.5 ml. pH is how much in the sense 5.4. Then now 50 ml we added. So far we have added 50 ml. Okay. Now what is the pH of solution? That let us find. Okay. Now initially what we took in the sense 50 ml of sodium carbonate of concentration 0.05 molar we have taken. On multiplying these two, we are getting millimoles of sodium carbonate. That is how much in the sense 2.5 millimoles. 2.5 millimoles of sodium carbonate we got. HCl we added from the burette to the conical flask. Totally what volume of HCl we added in the sense 50 ml. What is the concentration of HCl in the sense 0.1 molar? 0.1 molar. So on multiplying these two, we are getting millimoles of HCl. That is how much in the sense 5 millimoles of HCl we got. Now, this carbonate, conical flask carbonate takes H plus from HCl. Conical flask carbonate takes H plus from HCl and becomes a bicarbonate. Okay. This carbonate, how much we have taken initially in the sense 2.5 millimole we have taken. H plus how much we added so far in the sense 5 millimole we added so far. How much carbonate will convert into bicarbonate in the sense all 2.5, so remaining is 0. How much H plus will be consumed by carbonate in the sense 2.5, remaining is 2.5. Bicarbonate how much produced in the sense 2.5 millimole. Okay. The produced bicarbonate will consume this H plus and will become carbonic acid. So the produced bicarbonate consumes H plus and becomes what in the sense carbonic acid. Sir, bicarbonate how much produced in the above equation in the sense 2.5 millimole. H plus how much remaining in the above equation 2.5 millimole. So now they are reacting. Bicarbonate will react 2.5, remaining is 0. H plus will react 2.5, remaining is 0. So how much carbonic acid produced in the sense 2.5 millimoles of carbonic acid is produced. Okay. Now what is the volume of resultant solution? We'll see. Volume of resultant solution is how much we'll see. In the conical flask, initially we have taken 50 ml of sodium carbonate solution. From burette we have added HCl solution, that is how much in the sense 50 ml. Totally what volume we added in the sense 100 ml of solution we added. That 100 ml of solution added not. In the conical flask now 100 ml of solution is there. Set. So volume of resultant solution is how much in the sense 100 ml. In this, how much carbonic acid present in the sense 2.5 millimoles is present. Carbonic acid is a weak acid. Okay. Therefore, the resultant solution is what in the sense aqueous solution of this weak acid. How to find pH for this? That we will see. Now, resultant solution. Now, what is the resultant solution in the sense aqueous solution of carbonic acid? Aqueous solution of carbonic acid. How to find pH? For which this acid dissociation we consider. This acid is a dissociating. This acid is dissociating to give bicarbonate and H plus. This acid, carbonic acid, is dissociating to give bicarbonate and H plus. We can say this bicarbonate on further dissociating gives carbonate and H plus. We can say. Now we will see Ka for these two, Ka1 and Ka2. Will see for this we can say Ka2. Ka2 we can say that is 4.68 into 10 to the power of minus 11. For this we can say Ka1. Ka1 is 4.47 into 10 to the power of minus 7. Now see the equilibrium constant. This equilibrium constant itself 10 power minus 7. That means this equilibrium itself lies almost left. Then this equilibrium constant is roughly 10,000 times greater than that of this equilibrium. This equilibrium itself lies almost left side. Then is it necessary to consider this equilibrium also to find H plus concentration in order to say pH? Is it necessary? This equilibrium, is it necessary? It is not necessary, because this equilibrium itself almost left. Then what is the necessity of this equilibrium? So we need not consider this equilibrium to find concentration of H plus in this resultant solution in order to find pH. Okay. So we need not want the second equilibrium. So this equilibrium we need not consider now in order to find H plus concentration for finding pH of this resultant solution. Okay. So let us take this equilibrium alone. Okay. So we have taken this equilibrium alone. We have taken in this equilibrium, this carbonic acid initial concentration will say this carbonic acid present 2.5 millimoles present. What is the volume of resultant solution means 100 ml. So we got initial concentration of carbonic acid. Okay, it is a dissociating x molar. Therefore, how much remaining in the sense 2.5 by 100 minus x molar is remaining. Bicarbonate is x molar produced. H plus is x molar is produced. Okay. Now we will go for a acid dissociation constant Ka1, that is equal to bicarbonate concentration into H plus concentration by carbonic acid concentration. Now Ka1 is how much in the sense 4.47 into 10 to the power of minus 7. Now these two are equal, therefore we can say H plus square. We can say this here we can say x, we can neglect it because equilibrium constant is 10 power minus 7. So we can say 2.5 by 100 molar we can say. So carbonic acid concentration, carbonic acid equilibrium concentration we have written as 2.5 by 100. We have neglected this x. Why we have neglected this x in the sense equilibrium constant is 10 power minus 7. That means equilibrium lies almost left. Therefore, we are neglecting this x with respect to 2.5 by 100. Okay. So by simplifying this, we can get concentration of H plus. The concentration of H plus, how much in the sense 1.06 into 10 to the power of minus 4 molar. From this, we will find pH. pH is equal to 3.97. Okay, we got pH of the solution. So now we got pH of the solution, that is 3.97. 3.97 we got. Now in this solution, you see this solution here 50 ml of HCl we have added. What had happened on adding 50 ml of HCl? What happened? That we will see. Okay, so totally we added 50 ml. 50 ml of HCl we have added here. What we have taken in the conical flask? We have taken carbonate in the conical flask. Due to addition of HCl, carbonate has converted into bicarbonate. Then bicarbonate also completely converted into carbonic acid. See that? If you add acid into carbonate, what will happen? That we will see, then we will come to this place. Okay, we are taking carbonate. Any carbonate you take, sodium carbonate, calcium carbonate means limestone, zinc carbonate, ferrous carbonate, any metal carbonate you take, ammonium carbonate is not metal carbonate, it is a salt, non-metallic only. In the ammonium carbonate, all the elements are non-metals only. Okay, any carbonate you take, to the carbonate you add acid. This acid should have strength. This acid strength should be greater than or equal to carbonic acid. Okay. Carbonic acid is a weak acid. Its equilibrium constant, how much we said? 10 to the power of minus 7, Ka1. Ka2 is 10 power minus 11. Okay. So you are adding acid into the carbonate which has strength greater than or equal to carbonic acid. Then what will happen means carbonate will convert into carbon dioxide gas. It is a chemical reaction. Carbonate is converting into carbon dioxide gas. It is chemical reaction, we can say. Even bicarbonate, to the bicarbonate if you add so and so acid, this also will convert into carbon dioxide gas. So carbonate is converting into carbon dioxide gas, bicarbonate also converting into carbon dioxide gas on adding the acid which has strength greater than or equal to carbonic acid. So this is the chemical reaction here. That means in this titration, we are titrating between sodium carbonate and versus HCl. We are titrating between sodium carbonate versus HCl in the sense it is the chemical reaction. Sodium carbonate reacting with HCl and giving carbon dioxide. That's what happening. Okay, that means we have taken what initially in the sense sodium carbonate in the conical flask. We have added HCl. Carbonate is converting into bicarbonate. Then on further adding HCl, bicarbonate is converting into carbonic acid. Carbonic acid is nothing but carbon dioxide plus water. Carbonic acid is nothing but carbon dioxide plus water. Sorry, how do we say that carbonic acid is nothing but carbon dioxide and water? But we have written equilibrium like this. No, here equilibrium, carbonic acid equilibrium we have written like this and like this. Then how to write like this equilibrium? Means see the Ka1. What is the Ka1? 10 power minus 7. That means this equilibrium lies almost left. Almost left in the sense what? This carbonic acid has converted into carbon dioxide. That's what. Okay. So carbonic acid is having very low solubility. That's why very low solubility. How do we say in the sense 10 power minus 7? This solubility, let it be other factor. This carbonic acid Ka1 is 10 power minus 7. Therefore, its dissociation extent will be very less. So that this carbonic acid easily converting into carbon dioxide and water. So now we will see here. We have taken carbonate in the conical flask. We are adding H plus from the burette. When all the carbonate converts to bicarbonate, we can say this is called a equivalence point. We can say equivalence point. That means when all the carbonate is converted into bicarbonate, we can say equivalence point, provided that H plus should not be remaining. Okay, but H plus is remaining. Therefore, we need not consider this as equivalence point here. Suppose now we will see if carbonate is completely converting into bicarbonate while H plus is not remaining, then shall we say that point is called the equivalence point? Yes. Okay, when all the carbonate is converted into bicarbonate while no H plus is remaining, then we can say that point is called the equivalence point. So in this reaction, as per this one, we have added 50 ml of HCl, carbonate completely converted into bicarbonate. How much H plus remaining means 2.5 millimoles of H plus remaining. Bicarbonate, how much produced in the sense 2.5 millimole. How much carbonate you have taken? Everything is converted into bicarbonate, we said. Then this bicarbonate is taking H plus and becoming carbonic acid. Here in this step, all the bicarbonate has converted into carbonic acid and no H plus is remaining. That means the reaction is completely over. Therefore, we can call this is as a equivalence point. We can call this is as equivalence point. Why? Because bicarbonate completely converted into carbonic acid. H plus is not remaining. Nothing is remaining here. Bicarbonate is not remaining. H plus also not remaining. Everything is completely converted. Therefore, it is called equivalence point because reaction is over. Okay. Therefore, this point we can call it as a equivalence point. We can say. See. So far, in the acid versus base titrations, four types we have discussed: strong acid versus strong base, like this; weak acid versus strong base, like this, and all we discussed. In those places and all, we said equivalence point one time. Strong acid versus strong base titration means so and so place is called equivalence point. One time we said. But here you see, already we mentioned equivalence point at 25 ml. Again, we are saying equivalence point at 50 ml. Why? Because carbonate is bivalent. Bivalent in the sense, first this bivalent will convert into monovalent, that is called one equivalence point. So one first equivalence point is what? In the sense, in this place all the carbonate is converted into bicarbonate. That's what this equivalence point indicates. This first equivalence point indicates that starting is what? Carbonate. All the carbonate is converted into bicarbonate. That's what first equivalence point indicates. Then what about this equivalence point? It is called second equivalence point. This second equivalence point indicates that all the bicarbonate converts to carbonic acid. Carbonic acid means carbon dioxide and water. So carbon dioxide will be liberated. You might have seen this one. This to the carbonate, if we add acid, certainly brisk effervescence will come. In the salt analysis, suppose you are going for lab, you are doing salt analysis. In the sense, take carbonate, any carbonate you take, sodium carbonate will be available in the lab, certainly. To the sodium carbonate, you add dilute HCl. Brisk effervescence will come. Brisk effervescence means what? Carbon dioxide gas will be coming out. That means if you suppose you are opening the cool drinks bottle, in the sense, brisk effervescence will come. See, at the neck, you can see the brisk effervescence. That means dissolved carbon dioxide in the cool drinks comes out because of lowering of pressure. So that this bicarbonate is converted into carbonic acid, in the sense it is converted into carbon dioxide and water. That is the meaning. So in this place, in this second equivalence point, all the bicarbonate is converted into what we can say means carbonic acid, we can say. This is called second equivalence point. Okay. So since it is bivalent, we are saying that two equivalence point we are saying. Suppose trivalent means how many equivalence point you will get? 3 equivalence point we will get if it is trivalent. Like this will be there. So that we need not stick to the point that equivalence point means only one. We need not stick into that point. So we have to see the reactant and the reactants we have to see, and we have to see the products. As per that, we have to say equivalence point. We have to say that's all. So next, let us continue adding HCl. We will add HCl still more HCl. We will add. So far we have added 52.5 ml. So far we added 52.5 ml of HCl. Now what is the resultant solution? pH, that we will see. Now we are going for resultant solution pH. Okay. Sorry. Initially we took 50 ml of 0.05 molar sodium carbonate solution we have taken, that contains 2.5 millimoles of sodium carbonate. So far we added 52.5 ml of HCl, that has concentration 0.1 molar. This contains how much HCl, in the sense 5.25 millimoles of HCl is present. Sir. Now due to addition of HCl, what is the reaction takes place? That equation we will write. So now we will write bicarbonate. The first, initially carbonate only is there in the conical flask. So carbonate will take Initially carbonate is there in the conical flask, that is taking H plus and becoming what in the sense bicarbonate. Carbonate, how much we have taken initially means 2.5 millimole. Totally how much HCl we added so far in the sense 5.25 millimole. Now carbonate completely reacting, remaining is 0. HCl reacting 2.5 millimole. So how much HCl is remaining now, that we will see. How much HCl is remaining in the sense we can say this much HCl is remaining. Bicarbonate is produced to 2.5 millimole of bicarbonate produced. The produced bicarbonate takes H plus from HCl and becomes what in the sense carbonic acid. So bicarbonate how much produced in the before equation means 2.5 millimole. HCl how much remaining in the before equation means 2.75 millimole. It is reacting 2.5. It is reacting 2.5. So 0.25 millimole is remaining. And the carbonic acid how much produced in the sense 2.5 millimole of carbonic acid is produced. Okay. So now the resultant solution will take the resultant solution volume. We will see volume in the sense in the conical flask. Initially we have taken 50 ml of sodium carbonate solution. So far we have added HCl 52.5 ml we added. Therefore totally how much solution is there means 102.5 ml of solution is there. In the resultant solution, what is there means carbonic acid is present and HCl is present. Okay, so carbonic acid as well as HCl present. Now in the resultant solution, what is the equilibrium possible, that we will see. This carbonic acid is in equilibrium with bicarbonate and H plus. It is one equilibrium is possible. Okay, another equilibrium, bicarbonate gives carbonate and H plus. Okay, that equilibrium we need not consider. Okay, so we have considered this equilibrium. Now this equilibrium constant is 10 power minus 7. This indicates that this equilibrium lies almost left. Now this remaining HCl in the resultant solution will give H plus. That means HCl is a strong acid that is giving common ion to this equilibrium. Due to HCl giving common ion, the concentration of H plus in this equilibrium is getting raised. Therefore, equilibrium again shifting towards backward. Therefore, backward is highly favored in the sense this equilibrium is almost towards left. Therefore, in the resultant solution, H plus concentration we can take from HCl, not from this carbonic acid. This carbonic acid also giving H plus, but it is negligible when compared to HCl contribution. Therefore, in the H plus in the resultant solution, H plus concentration in the resultant solution is nearly equal to concentration of HCl. We can say carbonic acid also giving H plus, no doubt, but that H plus concentration we can neglect when compared to this concentration. Okay, sorry, HCl concentration we'll see, that is HCl how much present in the resultant solution means 0.25 millimoles present. 0.25 millimoles of HCl is present. What is the volume of resultant solution in the sense 102.5 ml. Okay, so we have substituted volume of HCl also. From this we can find what in the sense pH we can find. We can find a pH of the resultant solution. pH of the resultant solution is how much in the sense 2.61. Sir. So pH of resultant solution we got. pH of resultant solution is how much in the sense 2.6. 2.61 we got. Okay, let us add HCl further. So 55 ml we reached. Here pH is how much in the sense 2.32. Then again we will add 60 towards 60 ml we went. So now pH is 2.04. Okay. Now we have calculated a pH at a regular intervals. Here we calculated pH of the solution by considering carbonate hydrolysis. Here we have calculated pH of the solution by considering hydrolysis of carbonate. Okay. Here hydrolysis of carbonate we have considered. In this step we have calculated pH by considering carbonate hydrolysis. Next. Here we have calculated pH by considering buffer solution. Okay. Then Here we have calculated pH by using what formula, in the sense concentration of H plus is equal to square root of Ka1 into Ka2. Using this formula, we have calculated pH of the solution. Yes or no? During for 25 ml, for 25 ml case, we have found pH by considering square root of Ka1 and Ka2. We have found like this. Sorry. Next, here in this place, how we found H plus concentration, how we found pH, in the sense by considering buffer solution. Okay. Then at the second equivalence point, we have found pH. How, in the sense just aqueous solution of aqueous solution of carbonic acid we have considered, and we found pH of the solution. Okay. Here we found pH of the solution by considering HCl concentration. Okay. So in the first place, we considered carbonate hydrolysis. In this place, we have considered buffer solution. In this place, we have considered concentration of H plus is equal to square root of Ka1 and Ka2. Here buffer solution. Here aqueous solution of carbonic acid. That means weak acid solution. Weak acid solution here. Here HCl concentration. Every point is okay, but why here alone you have mentioned a special formula concentration of H plus equal to square root of Ka1 and Ka2? Because in this place, what is there, in the sense resultant solution contains bicarbonate. That bicarbonate is ambidented, so it can act as acid as well as base. Therefore, we derived so and so formula and we calculated pH. Okay. So when we have to use this formula, concentration of H plus equal to square root of Ka1 into Ka2, when we have to use, if the resultant solution, if the solution contains ambidented, means then we have to use. What is ambidented? Ambidented in the sense it can act as acid as well as base. Okay. Sir, we will see the example for that. For ambidented, we will see example. Now I will take bisulfate. This bisulfate can act as an acid. That means it will donate H plus and become sulfate. It can also act as a base. By taking H plus, it can become sulfuric acid. Okay. So it is ambidented. Then we'll see another example. We'll see HS minus I will take bisulfide. It is bisulfide. It will act as acid by giving H plus, therefore it becomes sulfide. It will act as base by taking H plus and become H2S. Okay, therefore it is ambidented. Now I will take another one. HPO4 2 minus I will HPO4 2 minus. Otherwise HPO4 minus I will take. H2 PO4 minus I will take. This will donate H plus and become a HPO4 2 minus. It is donating H plus, therefore acid. It is accepting H plus and becomes H3PO4. Okay, these are ambidented. So ambidented is present in the sense you consider that as acidic character as well as basic character, while we are using so and so formula. Concentration of H plus equal to square root of Ka1 into Ka2. Like this we are using. Sorry, okay. Now we got how to find pH of a solution in the titration of sodium carbonate versus HCl. Sir. Next, what is the suitable indicator for this titration? That we'll see. In this titration, we are having two equivalence point. We want which equivalence point, as per that we have to use the indicator. Suppose if you want first equivalence point, use the indicator which indicates color change at first equivalence point. Suppose if you want second equivalence point alone, use the suitable indicator which will indicate color change at second equivalence point. Suppose we want first equivalence point as well as second equivalence point. Then use suitable indicator that will give color change at first equivalence point as well as second equivalence point. Depending upon the requirement, you use it, sir. Now we will take which indicator will we can use in depending on the requirement. Okay, that we will see. Now we will take first phenolphthalein indicator. We will take that will give which equivalence point, that we will see. Okay, so phenolphthalein indicator we have taken, its pH range is 8.32 to 10 up to 8.3. Phenolphthalein gives colorless. From 10 onwards, phenolphthalein gives pink color. Okay, so we have taken phenolphthalein indicator. Its pH range is how much? In the sense 8.32 to 10 up to 8.3 pH. Phenolphthalein gives colorless. From 10 onwards, phenolphthalein gives pink color. Okay, now let us take sodium carbonate solution. Sodium carbonate solution is a colorless solution. HCl solution is colorless solution. Okay, so now we will add phenolphthalein into the conical flask solution. Okay, we have added phenolphthalein. So we added phenolphthalein indicator into the conical flask solution. pH of the conical flask solution is 11.5. Now phenolphthalein will give pink color if the pH is 10 and above. Okay, now conical flask is having pH 11.5. Conical flask solution pH is 11.5. As soon as phenolphthalein is added into the conical flask solution will remain colorless or will become pink. What do you think? Yes, it becomes pink. Okay, so phenolphthalein, as soon as phenolphthalein is added into the conical flask solution, the conical flask solution becomes pink color. Okay, let us continue titration. On adding HCl, pH is getting reduced. Here pink color will be there. Here pink color will be there. Here also pink color. Here also pink color. Okay, here also pink color will be there. Here what happens means intensity of pink color reduces slightly. Here also intensity of pink color reduces slightly. Here we can say phenolphthalein shows colorless. We can say that phenolphthalein gives colorless here. That means phenolphthalein indicates color change at first equivalence point. Therefore, using phenolphthalein, we can find first equivalence point. We can find using phenolphthalein, we can find what? In the sense first equivalence point we can find. Sir, so phenolphthalein we are using, we are finding first equivalence point. We are saying first equivalence point we are finding. Okay, next we will take a methyl orange. We are taking methyl orange indicator. We will take this methyl orange indicator is having pH range how much? In the sense 3.1 to 4.4. Up to 3.1 methyl orange gives red color. From 4.4 onwards methyl orange gives yellow color. From 4.4 onwards methyl orange gives yellow color. Now can we use this methyl orange indicator? That we'll see. Already we said, we concluded phenolphthalein. Using phenolphthalein we can say first equivalence point, we can say that we said. Now what about methyl orange? That we'll see. Let us add methyl orange here. So the pH of conical flask solution is how much? 11.5. Methyl orange will give yellow color if the pH is 4.4 and greater. Okay, so methyl orange is giving pH, methyl orange is giving yellow color if the pH of solution is 4.4 and above. Here conical flask solution pH is 11.5. That means this pH is greater than this 4.4. So methyl orange will give what color to the conical flask solution? Yellow color. So yellow color will persistent like this. Yellow color will persistent till this yellow color only will be there. Till this yellow color only will be there. Now what happens? Red color. So methyl orange gives a red color. That means methyl orange gives a color change at second equivalence point.